Section: Introduction. In this section, we aim to develop systems that can create videos for a wide range of uses, like making movies, creative storyboards, entertainment, AR, VR content, and robotics planning. Currently, the common method involves training video models on large datasets from the web. However, this approach often leads to videos that look dull, with poor colors, camera angles, and text-video alignment. This is not ideal for animators who want to bring scripts and sketches to life with accurate text adherence, consistent timing, and appealing camera views. Using general models may not meet these specific needs because they are trained on a wide variety of internet videos, which may not be suitable for particular tasks. So, how can we customize these models to produce high-quality videos that meet specific goals? Traditionally, aligning generative models in language and image domains starts with supervised fine-tuning, where the model is adjusted based on a target dataset. However, doing this for video generation is much harder and costly. Is there a different way to align video models without needing a target video dataset? Reward models, built on strong image or text models like Clip or BERT, are crucial for aligning image and text generations. These models can be fine-tuned with human preferences data or used directly to improve image-text alignment or object detection. How can we use reward models to enhance the video generation process? There are two main approaches: using reward gradients or relying on scalar feedback from the reward and estimated policy gradients. While using reward gradients directly can be more efficient, especially for high-resolution videos, text-to-image generation mostly uses gradient-free methods due to their quick training time. As we move from images to videos, the gap between reward gradient and policy gradient approaches widens due to the increased feedback specificity. We propose Vader, a method to adjust foundational video models using reward model gradients. Vader aligns various video models using pre-trained vision models and improves video and image-to-video generation. We also provide tips to enhance memory usage for training Vader on a single GPU. Our visualizations demonstrate that Vader significantly enhances model performance across tasks and outperforms methods like DPO or DDPO. Additionally, Vader can generalize well to new prompts not seen during training. Our code is accessible at the provided link. Section Summary. In this section, we explore the challenge of tailoring diffusion models to generate high-quality videos that meet specific task objectives, such as maintaining temporal consistency and desired camera perspectives. We discuss the limitations of conventional approaches that rely on large-scale datasets and propose using reward models to align video diffusion models effectively. Our proposed method, Vader, leverages reward gradients to adapt foundational video diffusion models, showcasing significant improvements in video generation quality across various tasks compared to methods that do not utilize reward gradients. Section: Related work. In this section, we will discuss the progress made in denoising diffusion models, which have shown significant advancements in generating images, videos, and 3D shapes. These models are typically trained using large unsupervised or weakly supervised datasets, giving them broad capabilities. However, for specific tasks like high-fidelity generation or precise text alignment, these models often need fine-tuning using likelihood or reward-based objectives. Likelihood objectives can be challenging to scale as they require access to specific behavior datasets. On the other hand, reward-based datasets are easier to collect since they only need human feedback on the generated data. By using pre-trained vision models as reward models, the process of reward fine-tuning becomes more accessible. The usual method for reward-based fine-tuning involves reinforcement learning through policy gradients. Recent studies have shown that directly backprop-agating gradients from the reward model to the diffusion process, instead of using policy gradients, can significantly improve sample efficiency. Some methods, like DPO, skip training an explicit reward model and optimize directly on human preference data. While this simplifies the process, it doesn't completely solve the sample inefficiency problem of policy gradient methods. Although progress has been made in aligning image diffusion models, aligning video diffusion models remains a challenge. In our work, we address this challenge by exploring how to align video diffusion models efficiently. We discovered that applying existing image alignment techniques to videos can lead to high memory usage. Instead, we propose using readily available image or video discriminative models to align video diffusion models. Our approach, VADR, Video Diffusion via Reward Gradients, focuses on adapting video diffusion models for specific tasks defined by reward functions. By leveraging the gradient structure of differentiable reward functions, we update the weights of the diffusion model efficiently. VADR allows flexibility in denoising schedules and prevents over-optimization by using truncated backpropagation. We consider various reward functions for aligning video diffusion models, such as image-text similarity reward, video-text similarity reward, image generation objective, and video generation objective. These reward functions help in aligning the generated videos with the desired tasks. To reduce memory overhead during training, we employ strategies like LoRa, mixed precision, gradient checkpointing, and subsampling frames. Our experiments demonstrate that VADR significantly improves the sample efficiency of fine-tuning video diffusion models, making the alignment process more manageable without requiring access to extensive video datasets. Section Summary. In this section, we explore the advancements in denoising diffusion models, particularly in aligning video diffusion models. These models have shown progress in generating diverse data types like images, videos, and 3D shapes through large-scale unsupervised or weakly supervised training. To cater to specific requirements like high-fidelity generation or text alignment, these models are often fine-tuned using likelihood or reward-based objectives, with recent methods focusing on backprop agating gradients from reward models to enhance sample efficiency. Section: Results. In this section, we focus on refining different conditional video diffusion models like VideoCrafter, OpenSora, Stable Video Diffusion, and Model Scope by using various reward models tailored for images and videos. These reward models include the aesthetic model for images, HPSV2, and PicScore for aligning images and text, YOLOs for removing objects, VideoMay for classifying actions, and VJEPA for ensuring temporal consistency. Our experiments aim to address several questions. How does VADR compare to gradient-free techniques like DDPO or DPO in terms of efficiency and computational demand? How well can the model adapt to new prompts not seen during training? How do the refined models compare to each other according to human evaluators? How does VADR perform across different image and video reward models? This evaluation helps us understand how effective VADR is in generating high-quality video content that aligns well with various input conditions. We compare VADR with methods like VideoCrafter, OpenSora 1.2, and Model Scope, which are state-of-the-art text-to-video diffusion models. We use them as base models for refining and comparing in our text-to-video experiments. For image-to-video experiments, we use Stable Video Diffusion as the base model, which is the current state-of-the-art image-to-video diffusion model. We also compare VADR with DDPO, a recent method for aligning image diffusion, and Diffusion DPO, which extends direct preference optimization, DPO, to image diffusion models. To fine-tune the video diffusion model, we utilize various reward models. The aesthetic reward model uses the LAION predictor V2 to score images based on aesthetics. Human preference reward models like HPSV2 and PicScore assess human preferences for generated images. We also have a reward model for object removal based on YOLOs and a model for video action classification called VideoMay. Additionally, we use VJEPA for ensuring temporal consistency in videos. We use different prompt datasets to fine-tune our models, including activity prompts, action prompts, and creatively designed text descriptions. For image-to-video models, we consider prompts from ImageNet categories and Stable Diffusion images. Section Summary. In this section, we focus on fine-tuning various conditional video diffusion models with a range of reward models tailored for images and videos, including aesthetic, HPS v2, PicScore, YOLOS, Video May, and VJEPA. Our experiments aim to compare Vader against gradient-free techniques like DDPO and DPO in terms of sample efficiency and computational demand, assess generalization to unseen prompts, evaluate models against each other, and test performance across different reward models for creating high-quality video content. We compare Vader with VideoCrafter, OpenSora, ModelScope, and Stable Video Diffusion as base models, and extend methods like DDPO and Diffusion DPO for aligning video diffusion models using reward models like aesthetic, HPS v2, PicScore, YOLOS, Video May, and VJEPA. Section: Sample and Computational Efficiency. In this section, we compare Vader's efficiency in terms of sample and computational aspects with other reinforcement learning methods like DDPO and DPO. We show the reward curves during training, where we plot the number of reward queries on the x-axis in the upper half of the figure and GPU hours on the bottom half. Vader proves to be more efficient in both sample and computation compared to DDPO and DPO because we send dense gradients from the reward model to the diffusion weights, while the other methods only backpropagate scalar feedback. We also evaluate the generalization ability of fine-tuning, which refers to the model's capability to perform well on unseen prompts after being fine-tuned on a limited set of prompts. We extensively test this across various reward models and baselines. For instance, when training text-to-video models, we use HPS v2 action prompts in the training set and activity prompts in the test set. Similarly, for image-to-video models, we train on the Labrador dog category and test on the Maltese category. Our results demonstrate Vader's strong generalization ability. Furthermore, we conducted a human evaluation study using Amazon Mechanical Turk to assess preferences between Vader and ModelScope. Participants were asked to compare videos generated by both methods based on text prompts and evaluate video quality. The majority of participants preferred Vader over the baseline methods, as shown in the results. We also provide visualizations of the generated videos for Vader and the baselines across different reward functions and base models. These visualizations highlight the improvements made by Vader in aligning videos with text prompts and its ability to generalize to unseen prompts effectively. Additionally, we showcase the results of fine-tuning models using various reward functions such as HPS, aesthetic, and PicScore. These visualizations demonstrate how Vader enhances text-video alignment and artistic quality in the generated videos. Moreover, we present videos generated after fine-tuning using the YOLOS-based object removal reward function, where objects like books are successfully replaced with alternative objects like blankets or bread. Lastly, we visualize the video generation process for action classification objectives using ModelScope and Vader. We show how Vader improves the distinction between different actions specified in the prompts, leading to higher rewards compared to misclassifications observed in earlier generations. Section Summary. In this section, we compare Vader's sample and computational efficiency with other reinforcement learning approaches such as DDPO and DPO. Vader demonstrates significantly higher efficiency in terms of both sample and computation due to sending dense gradients from the reward model to the diffusion weights, unlike the baselines that only backpropagate scalar feedback. Additionally, we evaluate Vader's generalization ability by fine-tuning on limited prompts and testing on unseen prompts, showcasing its preference over baseline methods in human evaluations and qualitative visualizations across various reward functions and base models. Section: VJEPA Reward Model. In this section, we present the results of increasing the length of the video created using Stable Video Diffusion, SVD. To generate long videos with SVD, we employ autoregressive inference. This means that the last frame produced by SVD serves as input to generate the next set of images. By carrying out 3 inference steps, we extend the context length of SVD by threefold. However, As we observe in the images highlighted in red, SVD begins to make errors in its predictions after just one inference step. This leads to distortions in the teddy bear's appearance or impacts the moving rocket. To address this issue, Vader utilizes the VJEPA objective with masked encoding to ensure consistency in the generated video. This approach effectively resolves discrepancies in both temporal and spatial aspects of the generated content, as illustrated in the accompanying figure.